Welcome back to the Deep Dive. Today, we're stepping into graph theory, and specifically a paper with a pretty intimidating title, Induced Subgraphs and Tree Decompositions, XVII, Anticomplete Sets of Large Treewidth.
Yeah, it does sound a bit daunting.
It does, but there's a really cool mystery in this paper, I think.
Yeah, it's like a mathematical whodunit, where the culprits are these graph structures that prevent the existence of anticomplete sets with large tree width.
Okay, so before we get lost in the jargon, can you remind us what treewidth and anticomplete sets actually mean like in the world of graphs?
Absolutely. So imagine a social network.
Okay.
The people in the network are like the vertices of our graph, and the connections between them, like friendships, are the edges.
Gotcha.
The tree width of this graph basically measures how tangled or interconnected this network is.
Okay.
A graph with low tree width would be like a small town where everyone knows each other pretty straightforward.
Yeah.
But a graph with high tree width is more like a sprawling metropolis with lots of different communities and complex relationships.
So high treewidth equals lots of complexity and interconnectedness.
Exactly.
Got it. Now, where do these anticomplete sets come in?
So an anticomplete set is just a pair of sets of vertices.
Okay.
Let's call them A and B, where no vertex in set A is connected to any vertex in set B.
Okay.
They're like two separate islands in our network archipelago.
So in our social network example, these would be two groups of people who have absolutely zero connections between them.
Yeah, exactly.
Interesting. But the paper isn't just looking at any anticomplete sets, right?
Right, you're right. It's focused on a very specific question. When does a graph with a large tree width contain two anticomplete sets that also have large tree width?
Okay.
It's like we're looking for complexity within complexity, hidden communities that are themselves intricate and interconnected.
Okay, I'm starting to see the puzzle here. So if a graph has high tree width, meaning it's complex overall, can we always find two separate complex subcommunities within it?
That's the million-dollar question.
Yeah.
And right from the start, the authors point to some obvious roadblocks, certain types of graphs that get in the way.
I'm picturing those super connected graphs where like everyone's friends with everyone else. Do those cause problems?
Exactly. Those are called complete graphs.
Okay.
They have a high tree width because everyone's connected.
Right.
But if you try to form two anticomplete sets within them, one of those sets is forced to be very simple, just a collection of isolated vertices with no connections between them.
Right, because if everyone's connected to everyone else,
Yeah.
you can't create two truly separate groups where no one knows anyone from the other group. One group will always end up being a bunch of loners.
Precisely.
What about those complete bipartite graphs you mentioned earlier? Don't they also have a high tree width?
They do. Think of it like two sports teams, where everyone on one team is connected to everyone on the other team.
Okay.
But there are no connections within the teams themselves.
Okay, I can see that. And if we try to form two anticomplete sets in this scenario, we run into the same problem, right? One of the sets would have to be just a single team with no internal connections.
Exactly. So complete graphs and complete bipartite graphs, despite having high tree width, don't allow for those special anticomplete sets we're searching for.
Right.
And what's remarkable is that Theorem 1.3 in this paper actually confirms our intuition. It tells us that apart from these two types of graphs, all graphs with a high enough tree width do contain those special anticomplete sets.
Wait, so they've actually proven that those two is the only roadblocks?
Yeah.
That's pretty amazing.
It is, and it gets even more intriguing. This theorem actually connects to a much older, unsolved problem in graph theory, known as the Elzahar and Erdős conjecture, which deals with coloring graphs.
Wow, so this seemingly technical problem about anticomplete sets actually has deep roots in some like fundamental mathematical questions. That's fascinating.
Yeah.
But before we get too deep into the weeds, you mentioned that the authors first proved this result in the context of induced minors, not just general graphs. Can you clarify what that means?
Of course. So think of it like this. A minor of a graph is a smaller graph you can create by deleting vertices or edges, or by contracting edges, which is like merging two vertices together.
Okay.
An induced minor, however, is a bit more restricted. You can only delete vertices and contract edges, no deleting edges directly.
Oh, okay.
This distinction is important because the authors first showed that if you can get one of those culprit graphs, a complete graph or complete bipartite graph, as an induced minor of a larger graph,
Yeah.
then that larger graph won't have the special anticomplete sets we're looking for.
So they essentially prove that if you can create one of those culprits by just deleting vertices and merging others,
Yeah.
you've stumbled upon a roadblock.
Exactly.
That makes sense. But I have a feeling this isn't the end of the story. Didn't you mention something about interrupted constellations?
You're right, the plot thickens. There's another more complex type of graph that also throws a wrench into the works, the interrupted constellation. These were originally studied by Bonamy et al., and they're quite fascinating in their structure.
Okay.
Imagine a central group of people represented by vertices with no connections between them.
Okay.
Now picture a single path, like a line of people, and each person in the central group is connected to at least one person on that path.
Okay. I'm picturing a starburst pattern with a line running through it.
You're getting the idea. The interrupted part comes from the specific way those connections are arranged.
Okay.
There's a pattern to how those central vertices connect to the path that makes these constellations special. And what's really sneaky is that this specific pattern is designed to prevent the existence of those two anti-complete sets with large tree width, even though the graph itself has high tree width.
So these interrupted constellations are like masterminds of disguise.
Yeah.
They have high tree width, but they're structured in a way that hides those complex anti-complete sets we're looking for.
That's incredible. They're like carefully constructed exceptions to the rule.
So now we have three potential culprits on our hands: complete graphs, complete bipartite graphs, and these mysterious interrupted S constellations. Is that the whole gang, or are there more hiding in the shadows?
That's the beauty of this paper. Theorem 1.4 comes in and declares, hold on, that's it. Those three are the only culprits.
Really?
It definitively solves the puzzle and provides a complete characterization of when a graph with high tree width will have those special anti-complete sets.
That's such a satisfying resolution.
Yeah.
So we now know that if a graph has high enough tree width and doesn't contain any of those three specific structures, then we're guaranteed to find those two complex separate communities within it. Incredible.
It really is a remarkable result, but the real magic lies in how they proved all of this.
Well, I'm all ears. Let's delve into those proof techniques.
Okay.
But before we get lost in the mathematical maze, can we quickly recap the main players in this mystery?
Absolutely. So we're looking for graphs with large tree width that contain two anti-complete sets, also with large tree width.
Right.
The culprits preventing this are complete graphs, complete bipartite graphs, and interrupted C-keys constellations.
Gotcha.
Theorem 1.3 essentially says that if a graph doesn't have any of those culprits as an induced minor, we're good to go. We'll find our special anti-complete sets.
Right.
And Theorem 1.4 builds upon this, saying that those three are the only things standing in our way.
Perfect. Now I'm ready to dive into the proofs and see how they built this airtight case.
Let's do it. All right, so let's unpack how the authors actually went about proving these theorems. It's a bit like a detective story, and we're going to follow the trail of clues they used to crack the case.
I love a good mathematical mystery. What's our first clue?
The first clue is this concept of strong blocks. Imagine a network of cities.
Right.
And between each pair of cities, you have multiple highways.
Okay.
Completely separate from each other, except at the cities where they intersect.
Okay, I'm picturing a very well-connected road network. Lots of options for getting between any two cities.
Exactly. Those cities, along with the bundles of independent highways connecting them, form what we call a strong block.
Okay.
And the paper relies on this pre-existing theorem, Theorem 2.2, which guarantees the presence of a strong block with certain desirable properties in any graph with a large enough tree width.
So they're using this existing knowledge about strong blocks as like a starting point, a foundation for their investigation. What does this Theorem 2.2 actually tell us?
It essentially says that if our graph is T-clean, meaning it doesn't contain any of those culprit subgraphs we talked about earlier, and it has a large tree width, then we're guaranteed to find a strong block within it that has a lot of cities and a lot of highways between each pair of cities.
Okay, so we've got our T-clean graph with large tree width, and we know it has this dense, interconnected, strong block hiding inside. How do we use this to find those special anti-complete sets we're after?
Here's where things get really clever. The authors focus on the edges between those bunches of highways. Imagine picking one point on each highway and connecting those points if there's an edge between the corresponding highways in the original graph.
So we're creating a whole new graph where the vertices represent these chosen points on the highways.
Yeah.
And the edges represent the connections between the highways themselves. That's pretty abstract.
It is. But this new graph, because of how it's constructed, ends up having a very specific structure. It forms what we call a linear model.
Okay, I have to admit I'm a little lost.
Yeah.
What exactly is a mu model?
Think of it like this. A my model is essentially a collection of sets of vertices, let's call them groups,
Okay.
where there's at least one edge connecting each pair of groups.
So there's a way of guaranteeing that these groups are all interconnected in some way.
Got it. And what's the significance of the linear part?
The linear part means that each of those groups is represented by a path like that line of people we talked about earlier. Okay, I'm starting to piece it together. So by cleverly choosing points on those highways in the strong block and connecting them based on the original graph's edges, they create this linear model. But why is this important? How does it help us find those elusive anti-complete sets?
That's where those famous Ramsey-type methods come in. Remember, Ramsey theory is all about finding order within seemingly random structures.
Right, like the idea that you can't have a room full of people without at least a few of them sharing a birthday. There's always some hidden pattern lurking beneath the surface.
Exactly. The proof of the theorem that establishes this connection between strong blocks and linear models, Theorem 3.1, relies on a couple of powerful results from Ramsey theory. The first one, Theorem 3.3, essentially says that if you have a large number of objects and you try to color them using a limited number of colors, you're guaranteed to find a large subset of those objects that all have the same color.
Okay, that makes sense intuitively. But how does coloring relate to graphs and models?
Think of the objects in this case as pairs of highways in our strong block. And the colors represent whether or not there's an edge between those two highways in the original graph.
So we're coloring each pair of highways based on whether they're connected or not in the original graph.
I like it.
Right.
And by applying this Ramsey-type theorem, the authors guarantee that they can find a large set of highways that all behave the same way. They're either all connected to each other or they're all not connected to each other. This is a crucial step in building that linear model.
Okay, so we've used Ramsey theory to find this nice orderly pattern within our strong block. But there was a second Ramsey-type theorem at play here, right?
There is, and this one is even more powerful. It's Theorem 3.4, and it allows the authors to find even more specific and intricate patterns within the strong block instead of just looking at pairs of highways. They're looking at entire sets of highways and ensuring that those sets connect to each other in very precise ways.
So we're going from pairs to whole groups of highways. And using Ramsey theory to ensure that these groups connect to each other in a very controlled manner. I can see how this would lead to a more complex model.
It does, and all of this clever manipulation of the strong block is ultimately in service of constructing a linear model, which, as we'll see, is a key stepping stone on the path to those anti-complete sets.
Okay, we've gone from a strong block to a linear model. What's the next step in this intricate dance?
The next step is to transform that linear model into something called a B-induced model.
Ah, another new term. I'm sensing a pattern here. But before we dive into that, can you remind me what the overall goal is? What are we trying to construct with all these models?
You're right. It's easy to get lost in the details. Remember, our ultimate goal is to prove Theorem 1.3, which states that if our graph doesn't contain any of those culprit subgraphs as an induced minor, then it must contain two anti-complete sets, each with large tree width.
Right.
The models we're building are stepping stones toward proving this theorem.
Right. So these models are tools for uncovering those hidden anti-complete sets with large tree width. Okay, now I'm ready to tackle the B-induced model. What does that even mean?
Think of it like two teams, A and B each, with multiple groups of people.
Okay.
A model, in its simplest form, has groups on side A and subs groups on side B. The key rule is that everyone in a group on one side must be connected to at least one person in every group on the other side.
Okay.
But there can't be any connections within the groups on the same side.
Okay, so it's like two teams facing each other, but instead of everyone being connected to everyone on the other team, it's more like each group sends out a representative to connect with each group on the opposing side.
That's a great way to visualize it. Now, the B-induced part means that Team B, one of those sides, has no connections within itself at all.
Okay.
It's just a collection of isolated individuals, each connected to at least one person in each of the groups on side A.
So Team A is interconnected within its groups, but Team B is just a bunch of individuals, each reaching out to multiple groups on Team A. Interesting. But how do we get from a linear model where each group is a path to this B-induced model?
That's the focus of section 4 of the paper, and it's quite a technical journey. They go through a series of steps, each outlined in a separate lemma using some very clever techniques.
The lemmas. So we're getting into the nitty-gritty of the proof. Now I'm ready to get my hands dirty. But before we dive into that, can you highlight any particularly interesting tools they use in this section? Any concepts that really stand out?
One particularly clever tool they introduce is the concept of an aligned model. Imagine you have that path, that line of people we talked about earlier, and you have other groups of people connected to it in a very specific way. It's like those other groups are aligned with the path.
Okay.
Each group has a designated section on the path where all of its connections to the path must occur.
Okay, so each group has its own territory on the path, and it can only connect to vertices within that territory. I like that analogy.
It's a helpful way to visualize it. And what's fascinating is that by leveraging these aligned models, the authors can either force the model to have a very controlled structure,
Okay.
or they can strategically split it apart into smaller pieces,
Okay.
ultimately leading to that B-induced model they're seeking.
So it's like they're playing a strategic game with these models, manipulating them to either conform to their desired structure or break apart into something more useful.
Exactly. And this entire process, from strong blocks to linear models to B-induced models, is all in service of proving Theorem 1.3, which, remember, is a key stepping stone to that grand finale Theorem 1.4.
We're getting closer to the big reveal, but I have a feeling there's still a lot of ground to cover before we get there. This B-induced model with its two teams and the isolated individuals on one side, that's not the final picture, is it?
You're right. We still have to tackle how they go from this half-induced model, where one side has no internal connections, to a fully induced model, where neither side has internal connections. That's where the real magic happens, and where we finally get to see those anti-complete sets with large tree width emerge.
All right, I'm on the edge of my seat. Lead the way to part 3. Welcome back to the deep dive. We're in the final act of our graph theory mystery, and I'm really excited to see how it all comes together.
Yeah, we've laid a lot of groundwork exploring strong blocks, linear U models, and those interesting B-induced models. Now we're finally ready to tackle Theorem 1.4 and see how it all culminates in the discovery of those elusive anti-complete sets with large tree width.
All right, let's do it. But before we jump into the theorem itself, can you quickly remind us why those B-induced models were so important? I'm still trying to wrap my head around how they fit into the bigger picture.
Of course. Remember, the B-induced model is like having two teams.
Right.
Where one team B is just a collection of isolated individuals, each connected to multiple groups on the other team, team A.
Right. The significance of this model is that it gets us halfway there. We have one side, team B, that has no internal connections.
Right.
Which is what we want in an anti-complete set.
Right, because in an anti-complete set, there should be no connections between vertices within the same set. But in a B-induced model team, A still has all those internal connections within its groups. So how do we get rid of those and create a truly induced model where neither side has internal connections?
That's the brilliance of section 5 of the paper.
Yeah.
The authors take that B-induced model and perform some incredibly clever manipulations using a combination of Ramsey theory and those aligned models we talked about earlier to essentially force the model to split into two completely independent sets.
Okay, I'm intrigued. Walk me through how they pull off this mathematical magic trick.
So they start with a very large B-induced model. Imagine Garian K is just ridiculously huge numbers representing a massive model with tons of groups on each side.
Got it. We're starting big, lots of groups, lots of potential connections. Exactly. Now they focus on that B side, the side with all the isolated individuals. They look for any individuals who happen to have connections to many different groups on the A side.
So they're searching for those individuals who are particularly well connected to the other team, those who have a lot of friends on team A.
Precisely. And here's the key. If they find enough of these well-connected individuals, they can use those connections to build a completely new BB model.
Okay.
Remember, a BB model would mean that both sides have those internal connections within their groups.
So by assuming there are too many of these well-connected individuals on team B, they create a contradiction. Because if they could build a BB model from that, it would violate the whole premise of starting with a B-induced model where one side has no internal connections.
That's the logic. They essentially force the model to behave by showing that if it doesn't behave, it leads to an impossible situation. It's a classic proof by contradiction.
I love those. They're so elegant. But how do they actually show that having too many well-connected individuals leads to that contradictory BB model?
And this is where Ramsey theory comes in again.
Yeah.
Remember how we colored pairs of highways earlier based on whether they were connected or not?
Yeah, that was a clever way to find those orderly patterns within the strong block.
They use a similar idea here. They color pairs of groups based on whether or not there's an edge between them. And by applying Ramsey's theorem, they guarantee that one of two things must happen. Either they can find a large set of groups on Team B that are all connected to the same set of groups on Team A, which would allow them to build that contradictory BB model.
Or drumroll.
Yeah.
They find a set of groups on Team B that are completely disconnected from each other internally.
You got it. And that's exactly what they need.
Yeah.
They've now found a section of the model where Team B also has no internal connections, effectively creating a fully induced model where neither side has connections within itself.
That's brilliant. They used the threat of creating a contradiction to force the modder into the exact structure they needed. It's like a mathematical game of chess.
It is. And once they have this fully induced model, they're almost there. Remember those aligned models where each group had its own designated territory on a path?
Yeah, like each group had its own lane on the highway, and they could only connect to vertices within that lane.
They utilized those aligned models again here. They cleverly split the paths in the model and used those split paths to construct two new constellations. And these constellations, because of the careful way they were constructed from that fully induced model, end up being anti-complete to each other.
Wait, so they've gone from this abstract model back to the actual graph itself.
Yeah.
And they've created two separate constellations that have no connections between them.
Exactly. And remember, these constellations weren't just plucked out of thin air. They were built from that special induced model.
Right.
Which means they inherit certain properties. Specifically, each of these constellations has an induced minor isomorphic to KTC.
KTC. That's a complete bipartite graph, right? One of our culprits.
It is. And the fact that both of these constellations contain KC as an induced minor means they both have a Treewidth of at least C.
Uh-huh. So they finally found those two anti-complete sets, both with large Treewidth. They've solved the puzzle.
They have. That's the proof of Theorem 1.3. And with Theorem 1.3 in hand, proving Theorem 1.4 is actually quite straightforward.
Okay, I'm ready for the grand finale. How does Theorem 1.4 follow from all of this?
It's like the final deduction in our detective story. They take a graph with large Treewidth and apply Theorem 2.1.
Okay.
This theorem essentially gives them two options. Either the graph contains two anti-complete sets with large Treewidth,
right,
which is what we want,
or it contains one of our three culprit subgraphs.
Precisely. So if the graph doesn't contain any of those culprits, it must contain those special anti-complete sets. It's the only remaining possibility.
That's incredible. It's such a satisfying conclusion to this mathematical journey. We started with this seemingly simple question about complexity within networks, and we ended up exploring this intricate world of strong blocks, models, Ramsey theory, and all these incredible clever proof techniques.
Yeah, it really highlights the power and beauty of graph theory. Sometimes the most straightforward questions lead to the most profound and elegant mathematics.
I have to say, I'm still a bit mind-blown by the sheer ingenuity of those proofs, but I feel like I've gained a whole new appreciation for the hidden structures and patterns within networks.
That's the magic of this field. It's all about uncovering those hidden connections and seeing the order within the apparent chaos.
And who knows what other mysteries are waiting to be solved out there.
Indeed. The world of graph theory is vast and full of surprises.
Well, on that note, I think it's time to wrap up this deep dive. My brain is officially full, but in the best way possible.
As always, it's been a pleasure exploring these fascinating ideas with you.
Until next time, keep those networks connected and watch out for those pesky interrupted slots constellations. Okay, getting right into it today. We're looking at this paper by Chudnovsky, Hijabi, and Sperkel. Induced subgraphs and tree decompositions. 7 color grow. Anti-complete sets of large Treewidth. Kind of a mouthful.
Yeah.
But really interesting stuff. They're basically exploring how the overall structure of a graph dictates whether or not these things called anti-complete sets exist.
Right, and they go beyond just like a surface level explanation. They really dive into the specific conditions that guarantee these anti-complete sets will exist, particularly when you're looking at graphs that have a high Treewidth. It's like they're searching for these hidden structures within these complex networks.
Yeah, exactly right. So for our listeners out there, maybe just a quick refresher. What exactly are anti-complete sets?
Okay, so picture a graph. You've got your vertices, you've got your edges. An anti-complete set is basically two groups of those vertices that are completely isolated from each other.
Okay.
Like there are no edges that connect any vertex from one group to any vertex in the other. It's like they're in separate universes within that graph.
Oh, like those awkward high school cliques that just completely ignore each other.
Exactly. So now the big question becomes, if we've got a graph that's already pretty complex, meaning it has a high Treewidth, can we always find two anti-complete sets within it that are themselves complex?
Hold on, wait. Before we go any further, I think we need to unpack Treewidth.
Yeah, good point.
What exactly are we talking about when we say tree width?
So tree width is essentially a measure of how much a graph resembles a tree.
Okay.
Now, trees are simple structures, right?
Yeah.
They branch out, but there are no cycles.
Right.
So a low tree width means the graph is relatively straightforward.
It's a family tree or something.
Exactly. But as that tree width starts to increase, things get more tangled, more interconnected.
So a high tree width means we're dealing with something more like a tangled jungle than a neatly organized family tree.
Exactly. And in this paper, the authors are interested in what happens in these jungles, these graphs, with high tree width. Can we always find two large self-contained sections that are totally disconnected from each other and are themselves complex?
Okay, so we're searching for these isolated yet complex subnetworks within these already complex graphs. What did the researchers find?
Well, they hit some obstacles right away. Certain types of graphs, like complete graphs and complete bipartite graphs, they kind of mess things up.
Oh, really?
How so?
What's so special about those types of graphs?
Well, think about a complete graph. Every single vertex is connected to every other vertex. It's like a giant party where everybody knows everybody else.
Yeah.
It's got high tree width because it's super interconnected, but you're not going to find two large, complex, anti-complete sets within it.
Interesting.
One of them will always end up being just a bunch of isolated vertices, what we call a stable set, not very interesting structurally speaking.
So complete graphs are kind of like those over-the-top social butterflies at a party. They're connected to everyone, but they don't really form distinct groups.
Exactly. And complete bipartite graphs, they pose a similar problem. Imagine two groups of vertices. Every vertex in one group is connected to every vertex in the other group.
Got it.
Again, high tree width. But you can't find two large, complex, anti-complete sets. One of them will always be a stable set.
Ah, I see. It's like two dance teams at a competition. They're all connected within their teams, but completely separated from the other team.
Precisely. So these complete and complete bipartite graphs are like the party poopers of the graph world.
They have high tree width, but they kind of mess up the whole two complex anti-complete sets thing.
Exactly.
Okay, so they hit this roadblock early on. Did they just give up?
Not at all. They are persistent researchers. They knew they needed a way to exclude these troublesome graphs, so they came up with this crucial result, Theorem 1.3.
Okay, I think this is where it gets really interesting. Tell me more about this.
Okay, so Theorem 1.3 basically states that if we can exclude those densely connected culprits, the complete and complete bipartite graphs, then any graph with sufficiently large tree width will have two anti-complete sets that both induce subgraphs with large tree width.
So it's like they're saying even in these most tangled, complex networks, as long as they're not those specific types we talked about, you're guaranteed to find these two large, independent, and equally complex sections that are completely disconnected from each other.
Exactly. It's a pretty powerful result. But their exploration didn't stop there. They uncovered another twist, a specific type of graph called an interrupted sex constellation.
Ooh, that sounds exotic. What are those like?
Imagine a graph with a central group of vertices that form what we call a stable set, meaning no edges connect them. It's like the calm center of the graph. Now, radiating outwards from the central group are a bunch of paths, like spokes on a wheel.
Okay, I'm picturing it, a peaceful center and paths branching out. But where does the interrupted part come in?
So the connections between those paths and that central stable set are arranged in a very specific way, like a carefully designed traffic system. There are bursts of connectivity, but with these strategically placed gaps or interruptions. And this arrangement limits how much any two sections of the graph can interact with that central stable set.
So it's like there are these roadblocks in the network preventing certain areas from being directly connected.
Precisely. And that's what's so sneaky about these interrupted constellations. They have large tree width because they have a lot of connections overall. But those strategically placed interruptions, they prevent any two large sections from becoming too complex on their own.
So they're like chameleons of the graph world. They kind of blend in and break the pattern.
You got it. And this discovery leads us to the climax of the paper, Theorem 1.4.
Drummer, please.
Okay, Theorem 1.4 essentially says that I have a graph with a large tree width avoids being any of the following: a complete graph, a complete bipartite graph, or one of those tricky interrupted sex constellations. Then, and only then, it absolutely must have two anti-complete sets, each inducing a subgraph with large tree width.
Okay, so this theorem is like the ultimate rule book. It tells us exactly when we're guaranteed to find those hidden structures.
Precisely. But what makes this work even more compelling is how they get to this conclusion. Their use of models to unravel this relationship is pretty ingenious.
Now, when you say models, What exactly are we talking about here?
Think of a model as a blueprint within a graph.
Okay.
It's a collection of pairwise disjoint connected induced subgraphs organized into two sets. One set has Rust subgraphs, the other has assumed. Now, the key here is that each subgraph from that first set has to have at least one edge connecting it to each subgraph from the second set.
Okay.
It's like a carefully orchestrated network of connections.
Okay. I'm starting to see how these models could be helpful in analyzing the structure of a graph.
Exactly. Now, the researchers took this a step further and focused on what are called linear models, where each of those subgraphs is a path.
Okay.
This simplification allowed them to apply some powerful tools from Ramsey theory.
Ah, Ramsey theory. Always a good time. But can we remind our listeners what it's all about?
In essence, Ramsey theory deals with finding order within chaos. It tells us that in any sufficiently large structure, even if it seems random, there will always be some predictable substructures hidden within it, like finding constellations in the stars. So the researchers are using Ramsey theory to find those hidden constellations within these linear models.
Interesting.
They were particularly interested in something called a strong KL block within these graphs.
Okay, let's break that down a little bit. What is a strong block?
Imagine you have a set of at least k vertices in the graph. Now, for each pair of vertices in that set, you have at least equal, completely separate paths connecting them. That's the basic idea of a KL block. The strong part comes in when we add the condition that any two paths from different pairs of vertices can only intersect at their shared endpoints.
Okay, so it's like a super connected subnetwork within the graph with multiple redundant pathways between these specific vertices.
Precisely. Now, proving the existence of these linear models in certain candidate graphs of sufficiently large tree width, this is where things get really interesting.
Okay, I feel like we're getting to the heart of their argument here. Walk me through it a little bit.
They essentially use Ramsey theory to demonstrate that those strong blocks, because of their inherent connectivity, will necessarily contain these linear models. And this connection is crucial because it links the existence of these models, which represent a certain level of structured connectivity, to the overall tree width of the graph.
So it's like they're using these strong blocks as a bridge between the local structure of the graph and its global complexity, measured by tree width.
Exactly. And this is just the beginning. From there, they delved into these half-induced models, which are kind of like stepping stones toward their final goal.
Okay, I'm intrigued. What's a half-induced model?
It's similar to a regular model, but with a little twist. In a half-induced model, one side, either the raw side or the side, consists of subgraphs that are pairwise anticomplete. It's like halfway to achieving a fully induced model where both sides have pairwise anticomplete subgraphs.
So they're gradually building toward those two complex anticomplete sets thereafter.
Exactly.
A fully induced model would essentially be proof of their existence, right?
Precisely. But to get there, they first had to prove that in a specific type of graph, one without a complete subgraph on A vertices, with a sufficiently large linear model, you can always find a linear B-induced model.
Hang on, can you break that down a bit for me? It's getting pretty dense.
Sure. Essentially, they're showing that if you have a graph with a certain level of connectivity represented by that large linear model, you can manipulate that model to guarantee the existence of a specific type of model, a B-induced model, which gets us closer to those anti-complete sets.
I see. So each step is like a strategic maneuver getting them closer and closer to their goal.
Exactly. But the proof of this step involved a series of increasingly intricate lemmas.
Okay. Well, let's dive into those lemmas in part 2. I'm ready for the next level of detail.
All right, so we're back and ready to dig into those lemmas that get us to Theorem 1.4. You know, the one that tells us exactly when we can expect those two large, complex, anti-complete sets within a graph.
Yeah, it's like we're putting together this giant mathematical puzzle. So let's talk about these lemmas. What's the first one we need to tackle?
Well, to prove Theorem 1.4, they first had to establish a few supporting results, right?
Right.
One of the key lemmas here is lemma 4.3.
Okay.
And this lemma, it aims to show that in graphs with a certain level of connectivity, represented by a large linear model, we can guarantee the existence of a B-induced model.
Okay, before we go any further, can you just remind me again what exactly a B-induced model is?
Sure. So remember that a B model is a collection of pairwise disjoint connected induced subgraphs, right? Split into two sets, one with subgraphs and the other with subgraphs. Now, in a B-induced model, the subgraphs on one side, the B side, are pairwise anti-complete.
Right, okay, so those subgraphs on the B side are like those isolated cliques we talked about before. There are no edges connecting them.
Exactly. And the proof of this lemma 4.3, it involves this clever inductive argument where these aligned models play a crucial role.
Yeah, those aligned models. I feel like they hold some key to unlocking this puzzle. Can you remind me what they are again?
Okay, so picture a model where you've got this long path, and then there are several sets of vertices that are attached to that path. If the model is aligned, it means that the order in which those sets attach to the path follows a specific pattern.
Okay.
And this pattern gives us leverage when we're trying to find that B-induced model.
So the alignment provides us with a sort of blueprint that helps us manipulate the model and extract the structures we're looking for.
Precisely. So in the proof of lemma 4.3, these aligned models are used to either control the overall structure of a model or to split it into smaller, more manageable submodels. It's a strategic divide and conquer approach.
Okay, so they're breaking the problem down into smaller pieces that they can then analyze more easily.
Exactly. And this technique is key to proving lemma 4.3, which then lays the groundwork for proving theorem 1.4. But before we get to that, there's another really important lemma we need to discuss, lemma 3.6. This one's a bit of a beast, but it's essential for understanding the relationship between those strong blocks and those linear models.
Okay, I'm ready for the challenge. Let's tackle this lemma 3.6.
All right, so lemma 3.6 is all about establishing a connection between those strong blocks and the existence of linear models. Remember those strong KL blocks we talked about?
Yeah, they're like those super connected subnetworks with all those redundant pathways between specific vertices.
Exactly, like the backbone of the graph, ensuring that connectivity. So lemma 3.6 really dives deep into the structure of these strong blocks, and it actually uses Ramsey theory not once but twice to reveal these hidden patterns within them.
Whoa, double Ramsey action. That sounds pretty intense.
It is. So the first application of Ramsey's theorem helps them identify a stable set within a specific strong block. Remember, a stable set is just a group of vertices with no edges connecting them.
Right, like those isolated cliques we keep talking about.
Exactly. And then they apply Ramsey's theorem again to further refine the structure of the paths within that strong block, ensuring a certain level of organized connectivity.
So they're using Ramsey theory like a fine-tooth comb, just teasing out these specific structures within these strong blocks.
Precisely. And this meticulous analysis allows them to establish a direct link between the existence of a strong block with certain properties and the existence of a linear model within that block.
So they're showing that if you have a strong block with these specific characteristics, you're guaranteed to find a linear model hidden within it.
Exactly. And this connection is crucial because it allows them to relate the local connectivity of the graph captured by those strong blocks to the global structure represented by those linear models.
It's like they're building a bridge between two different levels of analysis.
Exactly. And once they've established this connection, they can start piecing together the bigger picture leading towards the proof of theorem 1.4. But you know what? Maybe let's just take a step back and recap what we've covered so far.
Yeah, I think that's a good idea. My head's spinning a little bit with all these lemmas and models. A quick review would be helpful.
Okay, so we've established that the researchers are trying to figure out when a graph with a large tree width is guaranteed to have those two large, complex, anti-complete sets. And remember, early on, they hit that roadblock with complete and complete bipartite graphs kind of messing things up.
Right.
So they came up with theorem 1.3, which basically says if we exclude those problematic graphs, then any graph with a sufficiently large tree width will have those desired anti-complete sets.
Right. That was a major step forward.
It was. But then they discovered another tricky exception, the interrupted S constellations, which have a very specific structure that lets them avoid having those two large, complex, anti-complete sets.
Right, those chameleons of the graph world.
Exactly. So this led them to theorem 1.4, which essentially says that if a graph with large tree width avoids being a complete graph, a complete bipartite graph, or one of those interrupted constellations, then it must have those two anti-complete sets.
So theorem 1.4 is like the ultimate rule book.
Okay.
It tells us exactly when we can find those hidden structures.
Precisely. And to prove this theorem, they needed a few supporting lemmas, which is what we've been talking about. We discussed lemma 4.3, which uses the concept of aligned models to show that in graphs with a certain level of connectivity, we can guarantee the existence of a B-induced model.
Right, those B-induced models being those stepping stones towards those anti-complete sets.
Exactly. And then we got into lemma 3.6, which used Ramsey theory twice to establish that connection between strong blocks with specific properties and the existence of linear models within them.
Yeah, that was a real brain twister.
It was, but it's crucial for understanding how the local and global structures of these graphs are connected.
Okay.
So now, with all those lemmas in place, they're finally ready to tackle the main event, the proof of theorem 1.4.
Okay, I'm on the edge of my seat. Let's dive into that proofs in part 3. Okay, we're finally here. The moment of truth. After that deep dive into lemmas and models, we're ready to tackle the proof of theorem 1.4.
It all comes together beautifully. Remember, this theorem gives us that definitive answer to our question. When can we be absolutely sure that a graph with high tree width has those two large, complex, anti-complete sets?
Right, those hidden pockets of complexity we've been talking about.
Exactly. So the proof starts by assuming we have a graph that meets all the criteria. Large tree width avoids being a complete graph, complete bipartite graph, or one of those sneaky interrupted constellations.
So you're setting up a specific scenario for the proof.
Exactly. And from there, they leverage theorem 1.3, that earlier result we discussed. The one that says if we exclude those complete and complete bipartite graphs, any graph with a large enough tree width will have two anti-complete sets that induce subgraphs with large tree width.
Right, they're building on that foundation.
Exactly. So what they do is they show that if our graph fits the criteria of theorem 1.4, meaning it has that large tree width and it avoids those three structures, then it automatically satisfies the conditions of theorem 1.3.
So theorem 1.4 is like a special case of theorem 1.3 where those specific structures are ruled out.
Oh, precisely. It's a very elegant connection. And because our graph satisfies those conditions of theorem 1.3, we know it must have those two anti-complete sets.
But wait a minute, there's more to it, right? It's not just about finding any two anti-complete sets. We need to make sure that those sets also induce subgraphs that have a large tree width.
You're absolutely right. The proof goes a bit further to guarantee both those anti-complete sets have that complexity. They dive into this really detailed analysis with several parameters and some more clever uses of Ramsey theory.
This is where it gets really intricate.
It is. So picture this. We have a specific kind of model, a linear B-induced CoA model. And remember, in a B-induced model, one side, the B side, has those pairwise anti-complete sets.
Right, we've got those isolated sets on the B side with no edges connecting them.
Right. Now, on the other side, the A side, we have P paths. And they divide these paths up into groups of size, where A is another parameter we get to choose.
Okay, but why the grouping? What's the purpose of that?
That grouping is key to applying Ramsey theory. They define this mapping that essentially captures how paths on the B side connect to these groups of I paths on the A side. It's all about those connectivity patterns.
So they're looking for specific arrangements of connections between the two sides of the model.
Exactly. And then by applying Ramsey's theorem, they can guarantee the existence of a subset of those B side paths that have this very specific connectivity pattern to those I groups on the A side.
I think I see where this is going, but how do they make sure that those connections actually lead to anti-complete sets with large tree width?
That's where the careful selection of those parameters comes in. They show that this particular connectivity pattern, along with the fact that our graph avoids those three troublesome structures, leads to one of two possible outcomes.
Okay, what are those outcomes?
So the first outcome is that we end up finding an induced BB model in the graph. But remember, our initial assumption was that the graph avoided that type of model. So this outcome is a contradiction. It means our initial assumption was wrong.
So it's a dead end. It forces us to rethink things.
Right. Now, that second outcome is much more interesting. In this scenario, we can actually construct two anti-complete sets that induce subgraphs with Treewidth, at least C, where C is that level of complexity we were looking for.
So we got a fork in the road. One path leads to a contradiction. The other leads us straight to those complex anti-complete sets.
Exactly. It's a beautifully structured argument. Either our initial assumption was wrong or we hit our target. And because we set everything up so carefully, we know that first path leads nowhere, which means that second path has to be the right one.
It's a mathematical proof by elimination.
Exactly. And that elegant strategy, combined with all that analysis of the models and the parameters, it gives us a conclusive proof of theorem 1.4. It's really a demonstration of the power of careful step-by-step reasoning in mathematics.
Wow, what a journey. We've gone deep into this paper, uncovering those hidden structures, wrestling with those complex lemmas, and finally reaching this powerful theorem.
It's been great exploring this with you. Hopefully our listeners have a new appreciation for the beauty of graph theory.
Yeah, I'm sure they do. It's amazing how these concepts that seem so abstract can have real-world applications.
Absolutely. The ability to analyze and understand complex networks is so important in so many fields. Social sciences, computer science, biology, you name it. And who knows what other connections and applications are out there just waiting to be discovered.
Well, on that note, I think it's time for us to wrap up this deep dive. It's been a really exciting exploration of anti-complete sets Treewidth and how structure and complexity interact in these graphs.
And until next time, keep exploring, keep asking questions, keep those graph theory neurons firing.
That's all for this episode of The Deep Dive. We'll be back next time with another adventure in the world of knowledge and discovery. Welcome to The Deep Dive. Today we're going deep into graphs theory, specifically a recent paper by Chudnovsky, Hajibi, and Sperkel.
And what they're doing is they're grappling with this really intriguing problem about anti-complete sets and graphs that have large tree width.
Okay, so first things first, can you remind us what tree width is and why it's so important in graph theory?
Absolutely. So imagine that you're trying to deconstruct a really complex network, like a social network or a computer network. You're trying to represent it as a simpler tree-like structure.
Okay.
Tree width basically measures how much information is lost in that process.
Uh-huh.
So a low tree width means that you can represent the network pretty accurately as a tree.
Okay.
But a high tree width means it's a much more intricate structure and it's harder to simplify it.
Gotcha. So the higher the tree width, the more complex the graph.
Precisely. Now let's add another layer of complexity. Imagine you're trying to find two groups of nodes within this network where there are absolutely no direct connections between them.
Okay.
Those are your anti-complete sets. And the paper asks this very specific question. If a graph has a high enough tree width, meaning it's sufficiently complex, does that force it to have two anti-complete sets that are themselves complex, meaning they also have large tree width?
That's a great question. So it's kind of like we're looking for hidden independent communities within a sprawling metropolis
That's a fantastic analogy.
and trying to figure out if the city's overall design guarantees that those communities exist.
That's a really great way to put it. And the answer, as you might expect, is not straightforward. It really dives into this world of graph structure to try to figure out under what conditions this holds true.
So where do we even begin to tackle a question like this?
Well, a good starting point is to look for the obvious suspects,
Uh-huh.
graphs that have a large tree width but might not have the desired anti-complete sets.
So what are those usual suspects?
Well, the first culprits that come to mind are complete graphs and complete bipartite graphs.
Can you remind me what those look like? I always get those mixed up.
Of course, a complete graph is like a super connected network where every single node is connected to every other node.
Right.
Think of it like a small group of friends where everyone knows everyone else.
Okay, maximum connectedness.
Exactly.
What about complete bipartite graphs?
So those are a bit different. Imagine you have two groups of nodes, and every single node in one group is connected to every single node in the other group.
Okay.
But there are no connections within the groups themselves.
Okay.
So think of it like a matchmaking service where every client in group A is matched with every client in group B.
Okay, got it. So why are these graphs the initial roadblocks in our quest for these anti-complete sets with large tree width?
Well, because they certainly have large tree width due to their dense connections.
Right.
But when you try to find two anti-complete sets within them, at least one of those sets will end up being just a bunch of isolated nodes, what we call a stable set in graph theory terms.
Right.
And a stable set by definition has a tree width of 0. There are no connections, no complexity.
So they're like red herrings in our investigation.
Exactly.
They look complex, but they don't actually have the type of anti-complete sets that we're interested in.
They're a distraction. And that's where the real investigation begins. The researchers had to delve deeper beyond these obvious cases to uncover the underlying structures that do guarantee these anti-complete sets with large tree width.
So how did they move beyond these initial roadblocks? Did they find any clues that pointed them in the right direction?
Yeah, they did. One of the first major breakthroughs comes in the form of Theorem 1.3.
Okay.
This theorem states that if you exclude these complete graphs and complete bipartite graphs, any graph with a sufficiently large tree width must contain two anti-complete sets, each forming a subgraph of large tree width.
Okay, so that's pretty big. So does this theorem tell us exactly how large the tree width needs to be to guarantee these anti-complete sets?
It does. It gives us a precise bound based on the desired tree width of the anti-complete sets. So let's say we want to find two anti-complete sets, each with a tree width of at least 5. The original graph needs to have a tree width larger than a certain number that we can actually calculate.
That's pretty amazing. So they've found a concrete relationship between the tree width of the original graph and the existence of these special anti-complete sets.
Yeah, and it's a really important step forward.
So case closed, right?
Well, not quite. Remember how we talked about those initial suspects, the complete and complete bipartite graphs?
Right.
It turns out there's a whole other more elusive class of graphs that can also break the rule, even though they're not complete or complete bipartite.
Oh, what are those?
These are called interrupted 6 constellations.
Of interrupted 6 constellations. What do those look like?
So imagine a stable set, right? Which is just a group of nodes with no connections between them. Now picture a path, which is kind of like a straight line of nodes connected end to end.
Why?
An interrupted 6 constellation connects each node in the stable set to at least one node on the path, but in a very specific way. The connections are arranged so that no two nodes in the stable set share a common neighbor on the path.
Okay, so it's like each node in the stable set has its own dedicated connection to the path.
Exactly. It's like a carefully woven web of connections. But there's a rule that prevents any two nodes in the stable set from getting too close to each other.
Okay, and why are these constellations so important?
Well, because they can have arbitrarily large tree width, meaning you can make them as complex as you want.
Right.
But they're cleverly designed to prevent the existence of two anti-complete induced subgraphs, each having tree width 3 or more.
Okay, wait. Can you remind me what an induced subgraph is?
Yeah, of course. It's basically a subgraph that you form by choosing some nodes and including all of the edges between those nodes that were present in the original graph.
Right.
No adding or deleting edges allowed.
Right. So these interrupted constellations are kind of like masterminds of disguise.
Yeah, I like that.
They look complex because they have this high tree width. But they're hiding the fact that they can't produce those two anti-complete sets that are also complex.
That's exactly right.
So that brings us to the crux of the paper, right?
Yes.
How do we account for these constellations in our search for this definitive answer to this original question?
How do we overcome this new challenge?
Yeah.
And that's what we'll delve into in the next part of our conversation.
All right, I'm excited to learn more about that. I'll have to pick this up next time. Welcome back to our deep dive into the world of anti-complete sets and large tree width. Last time we left off with those half-induced models.
Yes.
Can you remind us why that's so crucial to this whole proof?
Of course. So remember, our ultimate goal is to prove this theorem 1.4, which basically says that if we exclude these complete graphs, complete bipartite graphs, and ample interrupted S constellations, then any graph with a sufficiently large tree width will have two anti-complete sets that themselves have a large tree width.
Right.
But to get there, we need this kind of stepping stone theorem. And that's theorem 2.1. And what theorem 2.1 does is it cleverly reframes the problem in terms of what are called ABC candidate graphs. And so these candidate graphs are defined by the absence of certain subgraphs and also, of course, the anti-complete sets that we're looking for.
Right.
And what theorem 2.1 states is that for any given A, B, and C, there's a maximum tree width that any ABC candidate graph can have.
Okay.
And if we can prove that we've essentially cracked the code.
So how do we actually bridge the gap between those half-induced models that we talked about last time and these fully induced ones?
So we make kind of a strategic move here. We actually flip the script. Instead of focusing on B-induced models where the paths in set B are pairwise anti-complete, we shift our attention to A-induced models.
Hold on. Why would we do that? I thought we were trying to find anti-complete sets in set B. Doesn't that kind of move us further away from our goal?
It might seem a little counterintuitive, I know.
Yeah.
But it's actually a clever maneuver. By focusing on these A-induced models, we can actually leverage the specific properties of these ABC candidate graphs to our advantage.
Okay, I'm intrigued. Tell me more about this flipping strategy. How does that actually work?
It starts with a careful analysis of this theorem 4.1, which basically guarantees the existence of a linear B-induced AM model in a chi-free graph. So chi-free means it doesn't contain a complete graph with A vertices,
Right.
with a sufficiently large linear model.
Okay, I remember that theorem. But how does that help us find this A-induced model?
Well, here's the key. If a graph has a linear B-induced O model, then it must also have a linear A-induced model. We literally just flip the roles of A and B.
Oh, I see. It's like looking at the same structure from a different angle.
Exactly. It's a really nice symmetry there.
Yeah.
And by applying theorem 4.1 and then just flipping the model, we automatically get our hands on an A-induced model, which turns out to be much more useful for our purposes.
Interesting. So this A-induced model is like our ticket to proving theorem 2.1.
Yes.
But how does an A-induced model actually lead to that conclusion that these ABC candidate graphs can't have arbitrarily large tree width?
So it's a multi-step process. First, we look at the branch sets of our A-induced model, and we divide them into two groups. Those where every vertex in a branch set has neighbors in fewer than B sets among the other branch sets, and those that don't.
Okay, so we're basically categorizing them based on how connected they are to the rest of the model.
Precisely. And by carefully choosing our parameters, these O and A values from the B-induced model, we can ensure that a substantial number of these branch sets fall into that first category.
The ones with more limited connection.
Exactly. And that's crucial because it allows us to apply this powerful lemma 4.4.
Okay, and what does that lemma do for us?
So lemma 4.4 basically offers us two possible outcomes.
Okay.
Either we can find this very highly structured submodel with a specific alignment.
Wait, alignment. That word keeps coming up. What does that actually mean in this context?
So an aligned model is basically one where the branch sets are connected to this particular path in a very organized way. So imagine a path that acts like a central spine, and then the branch sets are kind of attached in a specific order.
Okay, so alignment imposes a kind of order to the way these branch sets are connected.
It gives us the structure that we can then analyze more easily.
Gotcha. So what if we can't find this aligned submodel? What's the other option that lemma 4.4 gives us?
That's where things get really interesting.
Okay.
Because if we can't find this aligned submodel, then lemma 4.4 guarantees us something even better.
Okay.
The existence of a B-induced model.
Wait, I thought we were trying to move away from B-induced model.
We were, but remember, we're now working within an A-induced model.
Right.
So finding a B-induced model inside an A-induced model means we've essentially found an induced BB model.
Oh, I see.
Yeah.
It's like the double whammy. We start with an A-induced model.
Yes.
And if lemma 4.4 doesn't give us that aligned model, it hands us this induced BB model.
On a silver platter.
That's great.
But here's the catch. That induced BB model is actually a contradiction. Because remember, we're working within this ABC candidate graph, which by definition cannot contain such a model.
So we've kind of cornered ourselves into this situation where either outcome of lemma 4.4 leads to a contradiction.
Exactly. We've cleverly trapped ourselves.
That's brilliant.
And what this contradiction means is our initial assumption that an ABC candidate graph can have arbitrarily large tree width must be false. And by proving that ABC candidate graphs have a bounded tree width, we've essentially proven theorem 2.1, which was that key stepping stone to our main theorem.
That's impressive. It's amazing how this seemingly simple question about anti-complete sets and tree width has led us down this incredibly complex path of models and alignments.
It's a real testament to the power of this abstract reasoning.
It really is.
In mathematics.
Absolutely. And we're not done yet. We still have to connect all of this back to the original problem and actually prove that main result, theorem 1.4.
Absolutely. And that final step involves a fascinating detour into this world of constellations.
I can't wait to unravel those constellations. We'll have to continue our exploration next time. Welcome back to the final part of our deep dive. So we've been through these ABC candidate graphs, these linear models, even those tricky aligned models.
It's been a journey, hasn't it?
It has. It really has. So are we ready to tackle that grand finale?
I think so. The proof of theorem 1.4.
Okay, yeah, the main finding of the paper.
The main result.
Just to refresh our memories, can you remind us what theorem 1.4 actually says?
Of course. So it provides that definitive answer to our original question about these anti-complete sets and tree width. And essentially, it states that if we exclude complete graphs, complete bipartite graphs, and ample interrupted source constellations,
Right.
then any graph that has a sufficiently large tree width
Okay.
must have two anti-complete sets, each of which has large tree width itself.
And the proof, I'm guessing, weaves together all the threads that we've been following so far.
You got it. It
Yeah.
all comes together in this beautiful tapestry of logic and graph theory.
Okay, so where do we start? How do we connect all of these pieces to arrive at that final conclusion?
Okay, well, the first step is to recall Theorem 2.1,
Yep.
the one we spent so much time proving in Part 2,
Right.
which basically says that these ABC candidate graphs have a bounded tree width.
Right. Those candidate graphs were the ones defined by the absence of certain subgraphs, like the complete graphs and complete bipartite graphs.
Exactly.
And the anti-complete sets we're looking for.
Exactly. Now let's assume we have a graph G whose tree width is larger than that bound established by Theorem 2.1.
Okay.
So this means G cannot be an ABC candidate.
Right. So it must contain one of those forbidden subgraphs?
Yes.
Or it must contain the two anti-complete sets with large tree width that we're looking for.
Yes, exactly. We've really narrowed things down, haven't we?
Yeah, we have. So if G contains a complete graph or a complete bipartite graph, then we're done.
Yes. Those are two of our outcomes in the theorem.
Right. Okay, so the only remaining challenge is to figure out what happens if it doesn't contain those obvious culprits.
Right. And that's where those ample interrupted S constellations come in.
Okay.
But before we dive into those,
Yeah.
there's one more possibility we need to consider.
Okay.
What if G contains a structure that has a complete bipartite graph as an induced minor?
Ah, induced minors.
Yeah.
So those are formed by deleting vertices and contracting edges, but no edge deletions allowed.
Precisely. So it's kind of like a more restrictive version of a regular minor.
Right. And so if it contains a structure with a large enough complete bipartite graph as an induced minor.
Then it must also contain two anti-complete sets with large tree width.
Okay.
And that's actually a consequence of a previous result by the authors, which they actually reprove using Theorem 1.4 in this paper.
Oh, wow. So it's not only solving our main problem, it's powerful enough to actually reprove a previously established result.
It really speaks to the strength of the theorem.
Yeah, it does. So we've dealt with complete graphs, complete bipartite graphs, even induced minors of complete bipartite graphs. It's time to face those ample interrupted S constellations.
Head on.
Yes. How do we do that?
So this is where the paper delves into some really intricate analysis involving these properties of constellations. Specifically, they focus on constellations that are both ample and what we call Q-zigzagged.
Ample and Q-zigzagged. Those sound a little intimidating. Can you break those down for us?
Sure. An ample constellation, as we mentioned before, is one where no two vertices in the stable set share a common neighbor on any of the paths.
Okay.
It ensures kind of a level of independence between the vertices.
So ample prevents too much overlap.
Exactly.
Okay. What about Q-zigzagged?
So that's a little bit more technical. It basically imposes a limit on how many vertices in the stable set you can kind of bypass as you trace a path from one vertex in the stable set to another.
Okay, so it prevents the connections from becoming too tangled.
Right, too interwoven.
So these properties, ample and Q-zigzag, they're all about kind of controlling the structure of the constellation.
Exactly.
But how does that lead us to the final conclusion?
By carefully choosing the parameters for these properties, they are able to establish this crucial lemma. Lemma 6.2.
Okay.
And this lemma states that if you have an ample and sufficiently zigzagged constellation with specific parameters, then you are guaranteed to find two anticomplete sets within it, each with a large tree width.
So if our graph G contains such a constellation, then we've achieved our goal.
Yeah.
We found those two anticomplete sets with large tree width.
Exactly. And with that final piece in place, we've exhausted all the possibilities.
Right.
Our graph G has a large enough tree width. It must either contain a complete graph, a complete bipartite graph,
right,
an ample interrupted constellation with the right properties, or it must have those two anti-complete sets with large tree width.
That's it. That's the proof of Theorem 1.4.
That's the proof.
It's been a long and winding road, but we made it.
We did.
And we learned a lot along the way.
We did.
About this relationship between tree width and the structure of graphs.
Fascinating, isn't it?
It really is. It's incredible how these abstract concepts and these carefully crafted arguments can lead us to such profound truths about these structures.
I completely agree. And what I think is really fascinating about this whole paper is that it leaves us with this kind of tantalizing question.
Well, what's that?
Could there be other, even more exotic graphs out there that challenge this newfound understanding?
That's a great question to leave our listeners with. I think That's something that might inspire the next generation of graph theory enthusiasts to dive even deeper.
Exactly. There's always more to explore.
Absolutely. Well, this has been a fantastic deep dive.
It has.
Thank you so much for joining us, and we'll see you next time for another adventure in the world of knowledge and discovery. Welcome back, everyone. We're diving into a really cool research paper today. It's all about graph theory, specifically Treewidth and anticomplete sets.
Definitely a rich area, yeah. Lots of interesting problems there.
For sure. So we've both got the paper in front of us here, and it kicks off on page 1 by kind of setting the stage. First up is Treewidth. Now, we're all pretty familiar with that concept, but it's always good to refresh.
Right, of course. Treewidth is essentially a way to gauge the complexity of a graph, right? So a higher treewidth means you've got more intricate connections going on, potentially a bit more like a tangled web than a neat chain, you could say.
Exactly. And the central question this paper is tackling is, if a graph has really high treewidth, like super complex, does it have to have two big chunks, like subgraphs, that are also complex but totally isolated from each other, zero connections between them?
It's kind of intuitive to think, yeah, it would have to, right? Like if the whole thing's a mess, there must be these separate pockets of messiness too. But that's where it gets interesting, because it's not a simple yes.
Okay, so on that same page, they define anti-complete. Basically just two sets of vertices, and there are absolutely no edges connecting them.
Like think of two groups at a party who just absolutely refuse to mingle. They might be complex groups internally, but there's just no interaction between them whatsoever.
Got it. Then they bring up stable sets, which is a set of vertices where none of them are connected to each other within that set. They specifically mention this because it'll be important later.
Right, exactly. Stable sets are sort of a baseline for simple, right? Like if one of our anti-complete sets is just a stable set, it's not what we're looking for in terms of finding those separate pockets of complexity.
Then they bring up the grid theorem. And this theorem states that if a graph has a high enough treewidth, it's guaranteed to have a complex planar subgraph, and specifically a subdivision of a wall.
Right, and remember, planar just means you can draw it on a flat surface without any edges crossing over each other. And a wall is basically, you can picture it like a grid. A subdivision is where you essentially add more vertices along the edges of the grid, kind of stretching it out.
Right, right. But here's the thing, the grid theorem is talking about subgraphs in general. This paper, though, they're focusing on induced subgraphs, meaning you can't mess with the connections within the subgraph. It has to perfectly reflect how things are connected in the original graph.
Ah, okay. That definitely makes things a bit trickier. It explains why they point out complete graphs and complete bipartite graphs as kind of obvious exceptions to this whole two anti-complete complex subgraphs idea.
Yeah, let's break that down. A complete graph is where every single vertex is connected to every other vertex, just like super dense connections. And a complete bipartite graph is where you have two groups, and every vertex in one group is connected to every single vertex in the other group.
Right. So those are definitely complex structures, high treewidth for sure. But if you try to find two anti-complete sets within them, one of those sets is inevitably going to just be a stable set, no internal connections at all.
Because no matter how you slice them, you'll always have those connections between the groups.
Precisely. Okay, so moving on to page 2, we get to theorem 1.3. And this is one of the, the big results of this paper.
Yeah, this one states that if a graph has high enough treewidth, it either contains a large complete subgraph, a large complete bipartite induced minor, or it actually does have those two large, separate, complex subgraphs we were talking about.
Hold on. We got to define induced minor here. It's like a regular subgraph, but we're allowed to do something called edge contraction. Basically, you can take two vertices connected by an edge and just kind of merge them into a single vertex.
So it's like a condensed version of the subgraph, but still reflecting the connections from the original.
Exactly. So theorem 1.3 is saying our complex graph either has this big complete subgraph, a big complete bipartite induced minor, or it actually does have those two big separate complex chunks we've been wondering about.
They also tie this theorem to the Elzahar and Erdős conjecture about chromatic numbers.
Oh yeah, that is really interesting. Chromatic numbers, that's all about, coloring the vertices so that no two connected vertices have the same color. And that conjecture, much like this theorem, explores how complexity in a graph relates to these separable structures. It's a cool parallel.
Okay, so then they pose this kind of key question, right? Do those complete bipartite graphs really need to appear as induced minors? Could they maybe just be regular induced subgraphs?
Yeah, that's the question that kind of drives the rest of this whole paper. And the answer lies in the special type of graph they introduce on page 3. They call it an interrupted stints constellation.
This is where things get really interesting. The definition of an interrupted stints constellation, I got to be honest, it's a bit dense. But thankfully, they give us a visual in figure 2.
Right, so imagine like a path, right? Just a straight line of connected vertices. Then we have this separate group of vertices, all unconnected to each other. Each one of those lonely vertices, you could call them, has at least one connection to the path, but no two of them share the same connection point.
Okay, so it's like a path with these isolated vertices kind of orbiting it.
Exactly, and it's interrupted because of the specific arrangement of how those connections to the path are laid out. Like if you look at figure 2, you'll see there's a very distinct pattern to it.
All right, so what makes these interrupted constellations so special?
Well, they have a few crucial properties. Firstly, they don't contain certain complete subgraphs, specifically K4 and K33. Those are complete graphs on 4 and 6 vertices, respectively, with K33 having a bipartite structure. But, and this is important, they do have a large, complete bipartite induced minor.
Wait, didn't we say those complete bipartite graphs were kind of the exceptions?
We did, and that's the crucial distinction here. Interrupted S constellations, they have that structure as an induced minor, not as a regular induced subgraph.
Ah, there's that subtle difference again. And so these interrupted 6 constellations, they don't have 2 anti-complete complex subgraphs.
Nope, they don't. They're like the exception that proves the rule, you know?
This all leads to theorem 1.4, which basically gives us the complete answer to our original question, right? Conference graphs either have simple culprit subgraphs, like complete or complete bipartite ones, or they have an interrupted S constellation. Or they actually do have those 2 separate complex subgraphs.
Yeah, it's a really elegant result. And the authors actually point out that this theorem kind of builds upon theorem 1.3 and even simplifies a proof from a previous paper. It really shows how research builds on itself, you know?
That's sure. Okay, I'm ready to dive into the proof itself. They start laying out their tools on page 4.
Right. They introduce these concepts of models, linear models, and strong blocks. They're like the building blocks of their mathematical argument.
Can you give us like the intuition behind these concepts without getting too lost in the formal definitions?
Sure. So a model is essentially like a structured way to represent certain relationships within the graph. And a linear model specifically uses paths, like those lines of connected vertices we talked about, as its core components.
Okay, so like a simplified blueprint of some of the connections in the graph.
Exactly. And a strong block is basically a cluster of vertices with tons and tons of paths between them. It's a region of like really high connectivity.
Got it. And then they use theorem 2.2 to guarantee that our complex graph actually is a strong block with specific properties, like setting the stage for the proof.
Right. And then the rest of pages 4, 5, and 6 is basically outlining their proof strategy. They're going to show that we can kind of ignore certain types of edges within this strong block and just focus on the edges that lie between paths.
So they're kind of narrowing down the possibilities right from the get.
Exactly. And this all leads to the existence of a linear model, which they'll analyze in detail later on.
Okay, then on pages 7 through 10, it's like Ramsey theory enters the picture.
Ah, yes. Ramsey theory, such a powerful tool for finding order, even in the most seemingly random or chaotic structures, you know?
I mean, I know the basics, but could you maybe give a quick example of how it works?
Sure. So imagine you have 6 people at a party, right?
Yeah.
Ramsey theory guarantees that you'll either find 3 people who all know each other or 3 people who are all complete strangers. It's all about finding these unavoidable patterns in relationships.
Right, right. So how does that apply to our graph proof here?
Well, they use a specific result from Ramsey theory, lemma 3.6 to be precise, and they use this to rule out certain types of edges within our strong block. It helps simplify the whole structure they're working with, you see.
So it's like using Ramsey theory to clear away some of the clutter.
Exactly. And this leads to a major milestone, which is theorem 3.1. This theorem proves that our complex graph absolutely must contain a special structure called a linear model.
Excellent progress. Now, pages 11 through 15 bring in this concept of aligned models.
Right. So an aligned model is kind of like a linear model, but with a specific property. It's like all the connections from other parts of the graph are neatly organized at one end of the paths that make up the model. Think of it like paths where all the side roads kind of converge at one end.
Okay, yeah, I can picture that.
Yeah.
So how does this help us?
Well, Lemma 4.4 uses alignment to either find a very nicely structured model, which is great for our purposes, or it allows us to break down our model into smaller, more manageable pieces.
Classic divide and conquer strategy.
Precisely. And this leads to another victory, which is Theorem 4.1. We now have what's called a half-induced model.
Half-induced, what does that mean?
It means that one side of our model has that nice, organized alignment that we were talking about.
Okay, so we're getting closer to our goal here.
Absolutely. And then pages 16 and 17 is where things really come to a head. Remember those aligned models? Well, they use alignment again to force our graph into one of two scenarios.
Lay it on me.
Scenario 1. Our graph finally reveals those two anti-complete complex subgraphs that we've been searching for this whole time. It's like they were hiding in plain sight.
Okay, and scenario 2.
Scenario 2. We find a complete bipartite induced minor lurking within the graph. Remember those exceptions we talked about earlier? They're making a comeback here.
So no matter what, we're guaranteed to find one of those two outcomes.
Yeah.
No other possibilities.
That's the beauty of this part of the proof. Each step systematically eliminates other possibilities, leading us inevitably to one of those two conclusions. It's like a carefully crafted mathematical dance, you know.
I like that, a mathematical dance. And this all ties back to Theorem 2.1, right?
Exactly. Theorem 2.1, which we saw earlier, is formally proven through this whole intricate process of aligning models, eliminating possibilities, and ultimately forcing the graph to reveal its secrets.
It's really incredible how it all fits together. But the paper's not done yet, right? We still have pages 18 and 19 to cover.
Right. Those final pages deal with Theorem 6.1, which introduces these concepts of interrupted and zigzagged constellations. They're variations on those interrupted sesquil constellations we discussed before.
Okay, yeah, remind me, what were those constellations all about again?
Remember those lonely vertices connected to a path? So interrupted constellations have a very specific order to those connections. Zigzag constellations have a bit more flexibility in how those connections are arranged, but still with some restriction.
Right, right. I remember those diagrams. What's the significance of these new types of constellations then?
Well, they're essentially the building blocks for the final result of the paper. Lemma 6.2 shows that a highly zigzag constellation, meaning lots of back and forth connections, absolutely must contain those two anti-complete complex subgraphs we're after.
So we're using these constellations to, like, force the graph into revealing those subgraphs.
Precisely. And that brings us full circle back to Theorem 1.4, the ultimate answer to our initial question. We've gone through the complexities of complex graphs, explored the power of Ramsey theory, and uncovered the secrets of these intricate constellations, all to arrive at this really satisfying conclusion.
That was quite a journey through graph theory. Can you maybe summarize the key takeaway for our listeners who might be feeling a bit overwhelmed by all the details?
Of course. The main takeaway is complex graphs, they're fascinating, they're intricate, but they still have these predictable structures hiding within them. We've shown that if a graph is complex enough, it will either have some obvious, easily identifiable substructures, like those complete or complete bipartite graphs, or it will inevitably contain those two large, isolated, complex subgraphs we were talking about.
So even in the most complex systems, there's this underlying order, a hidden structure just waiting to be discovered.
That's exactly it. It's the beauty of mathematics, you see. It gives us the tools to uncover patterns and make sense of seemingly chaotic structures. But here's a final, kind of provocative thought for our listeners. What if we relax the rules a bit?
What do you mean?
What if instead of demanding those two complex subgraphs be completely isolated, we allowed, like, a few connections between them?
So like those rival groups of the party suddenly have a couple of intermediaries kind of bridging the divide.
Exactly. How would that change our understanding of complex graphs? Would we still find those predictable structures? That's a question worth exploring.
It really is. It's fascinating how even after solving one problem, mathematicians always find new questions to ask. It just never ends.
That's the nature of the field, Always more connections to make, more structures to uncover.
Well, on that note, I think we've given our listeners plenty to think about today. This paper was quite the deep dive into the power of graph theory, showing how it can reveal the hidden order within complex systems.
It really highlights that even in the most intricate networks, there are these predictable patterns just waiting to be discovered.
Absolutely. And who knows, maybe this deep dive will inspire some of you to explore what happens when we relax those rules and allow for those connections between those anti-complete subgraphs.
That would certainly be a fascinating avenue of research.
It definitely would. So to our listeners out there, keep that curiosity alive and keep exploring. The world of complex networks awaits.
Until next time, let me know if you need further parts of the transcript rewritten for TTS.
Welcome to the Deep Dive. Today, we're diving deep into this pretty dense paper. It's called Induced Subgraphs and Tree Decompositions, XVII. Anti-complete sets of large tree width. We're going to be exploring the connections between a graph's tree width, that's a measure of its complexity, and the existence of anti-complete sets within it. So, you know, those sets of vertices with no edges connecting them.
Right.
Our mission today is to answer this pretty intriguing question. If a graph is complex enough, can we always find two large, intricate subgraphs within it that are completely disconnected from each other? And the answer is more nuanced than just a yes or no. There's some really fascinating exceptions that reveal a lot about the underlying structure of graphs. So let's dive right in. Now, you, the listener, are a math aficionado, so we can skip Graph Theory 101 and jump straight into the core concepts. The paper kicks off by setting the stage with Treewidth and its significance. They reference a pretty well-known theorem, the grid theorem, formerly known as Theorem 1.1. It states that a graph with sufficiently high tree width must contain a large grid-like structure, a subdivision of a wall graph to be precise. So this theorem highlights a link between a graph's overall complexity, represented by its tree width, and the presence of specific substructures. It's like saying, if a graph is complex enough, certain patterns are bound to emerge.
Yeah.
Now, this deep dive is on a similar quest. But instead of grid-like structures, we're interested in induced subgraphs and whether we can always find two large, complex, anti-complete sets within them.
Okay.
The first major result we encounter is Theorem 1.3. It states that for any desired level of complexity, a graph with sufficiently high tree width will almost always have two large anti-complete sets. But that almost is key here. There are exceptions, and they're not what you might initially expect. Instead of just saying there are exceptions, the theorem lays them out explicitly. The first exception is a large complete graph, denoted as Ka. Every vertex in a complete graph is connected to every other vertex, so finding two disconnected sets is impossible.
Right, makes sense.
The second exception, though, is a bit more intricate. It's a large complete bipartite graph, represented as KB, appearing as an induced minor. Now, this distinction between a minor and an induced minor, that's crucial, and the paper goes into quite a bit of detail about it.
Yeah.
So, to refresh our memories, a minor of a graph can be created by removing vertices or edges, or by contracting edges, which gives us a lot of flexibility in manipulating the structure. An induced minor, however, is more restrictive. We can only remove vertices or contract edges. No direct edge removals allowed.
Okay.
This constraint ensures that the complete bipartite structure is genuinely embedded within the graph, not just a result of our edge manipulations. Now, you might be thinking, okay, complete graphs and complete bipartite graphs, sure, those make sense as exceptions, but are there any other curveballs? And the answer is a resounding yes. There's a third, far less obvious exception that really throws a wrench into things, the interrupted constellation. This one's a bit of a head-scratcher, but it's key to understanding the nuances of this relationship between tree width and anti-complete sets. To grasp this exception, picture a path, just a simple linear sequence of connected vertices.
Okay.
Then imagine a separate set of vertices, called a stable set, where no two vertices within this set are connected to each other. Now, each vertex in the stable set has at least one connection to the path, but here's where the interrupted part comes in.
Okay.
If we number the vertices in the stable set and draw a path connecting any two of them that goes to the main path, think of it like a path that zigzags between two of those unconnected vertices, but it has to pass through that main line of vertices. And the interrupted property means that every vertex in the stable set that comes after the two we connected must have a connection to that zigzagging path.
Okay.
The paper includes Figure 2 to help visualize this, and I highly recommend taking a look. So what makes this interrupted S constellation so special, so exceptional?
Well, it doesn't contain any large complete graphs, like K4, or complete bipartite graphs, as induced subgraphs like K33. And second, it has large tree width, meaning it's complex enough to meet the criteria of our initial question.
So it fits the profile.
Yeah.
But here's the kicker. It doesn't have those two large anti-complete sets we were looking for. It's like this structure found a loophole to avoid having those anti-complete sets.
Right.
While still being quite complex.
Precisely. And that's why it's so important. It forces us to refine our understanding and look beyond the obvious exceptions.
So does this mean our initial theorem 1.3 is wrong?
Not at all.
Yeah.
It simply means we need a more nuanced answer, one that accounts for this unexpected exception. That's where theorem 1.4 comes in.
Okay, so theorem 1.4 is the upgraded comprehensive understanding.
Yeah.
Right, what does it say exactly?
Okay, theorem 1.4 states that every graph with sufficiently high tree width must contain at least one of the following: a large complete graph, a large complete bipartite graph, a large interrupted S constellation, or, finally, two anti-complete sets with large tree width.
So we finally have our definitive answer. If a graph is complex enough, it either has one of these specific structures or gives us the two large, disconnected subgraphs we were searching for.
Exactly. This theorem provides a more complete picture of the relationship between tree width and the existence of these anti-complete sets. It's quite elegant, really.
Absolutely. Now, I know our listener is a fellow math enthusiast who enjoys a good challenge. So let's shift gears a bit and pick into the proof techniques themselves.
Okay.
I know the proofs are quite involved, but are there any highlights that might be particularly intriguing?
Well, one of the first things you'll notice is the use of Ramsey theory.
Oh yeah, Ramsey theory.
Particularly theorems 3.3, 3.4, and 3.5. These theorems are all about finding order within seemingly chaotic structures.
Ramsey theory always seemed a bit mind-boggling to me. Could you give us an example of how it's used here?
Imagine a vast number of vertices, and you're trying to figure out their connections. Ramsey theory says that if you have enough vertices, you're guaranteed to find either a large set of vertices that are all connected to each other, or a large set that are all disconnected.
So even in a seemingly random network, there are bound to be clusters of order, whether through connection or lack of connection. That's a fascinating concept.
Exactly. And this principle is used extensively in the proofs. To pinpoint specific structures within the graphs being analyzed, it's a powerful tool for imposing order on complexity.
So Ramsey theory helps us find order in the chaos. But what other tools do the mathematicians employ here?
Another key concept is that of strong blocks, which are essentially highly connected substructures within a graph. Theorem 2.2 in the paper establishes that if a graph has high enough tree width and doesn't contain certain specific structures, then it must have a strong block of a certain size.
So it's another way of saying that complexity forces the emergence of specific patterns, in this case, densely connected strong blocks.
Precisely. The paper uses these strong blocks as building blocks for finding either the desired anti-complete sets or those specific exceptional structures, like interrupted on constellations.
It seems like there's a recurring theme here. That complex graphs, despite their seeming randomness, exhibit predictable patterns.
You're catching on. And that brings us to one final technique I'd like to highlight, the concept of alignments.
Okay, alignment.
This technique explores how different parts of a graph attach to each other.
So by studying these attachments, the mathematicians can either locate the anti-complete sets or reveal the presence of those special structures.
Exactly. By meticulously piecing together these clues from alignments, Ramsey theory, and strong blocks, they either uncover the desired anti-complete sets or expose the specific structures that prevent their existence.
This is really fascinating stuff. It feels like detective work. Using these mathematical tools to unravel a complex knot and reveal the hidden order within it.
That's a great analogy. Now, to truly appreciate the power of these techniques, we need to dive into the actual proofs themselves. And that's exactly what we'll do in part 3 of our deep dive.
I can't wait. We'll be back after a short break to explore the intricate details of those proofs and see how those anti-complete sets finally emerge. All right, we're back, ready to tackle the heart of the paper, Section 5. This is where the authors bring all those intricate concepts together and answer our burning question about anticomplete sets and tree width. They really build up the suspense, don't they?
They do. Section 5 is where the magic happens. It's the culmination of all the groundwork laid in the previous sections.
Yeah, we've got our toolbox filled with Ramsey theory, strong blocks in those half-induced models. What's the strategy for this final act?
The main goal is to prove Theorem 2.1, which, if you recall, is essentially equivalent to Theorem 1.3, the one that stated a graph with high enough tree width will almost always have two large anti-complete sets, unless it contains one of those special structures.
Right. Those exceptions were the complete graphs, the complete bipartite graphs as induced minors, and the enigmatic interrupted S constellations.
Exactly. Now, the proof of theorem 2.1 is like a grand finale, bringing together all those techniques we discussed.
Okay. Take us through the highlights. How does this mathematical symphony unfold?
They begin by assuming they have an ABC candidate graph, meaning it's free of the exceptions we just mentioned, and has a tree width larger than a carefully chosen value, F2.1, which depends on A, B, and C.
So they're setting up a scenario where the graph is complex enough that it should have either those anti-complete sets or one of the special structures. It's like a mathematical if this, then that statement.
Precisely. Using theorem 3.1, they know this graph must contain a linear model. Then applying theorem 4.1, they can find a linear B-induced model within that model. Remember, B-induced means one side of the model is self-contained.
And O and A represent the number of paths on each side of the model. It feels like they're carefully setting the stage piece by piece.
Yes, and the values of Gay and Galley are strategically chosen based on those initial parameters, A, B, and C. With this half-induced model in hand, they start their search for either those anti-complete sets or the structures that prevent their existence.
Okay, this is where it gets really interesting. How do they actually pinpoint those anti-complete sets?
It's a two-pronged approach based on analyzing the connections within the model. First, they divide the model into two sets of paths, the A side and the B side.
Then they examine how the paths on the B side connect to those on the A side, looking for those islands of disconnectedness.
Exactly. If the connections between the A side and B side are relatively sparse, they can apply Ramsey theory to find two large sets of paths, one on each side, that are completely disconnected. Those are our anti-complete sets.
But what if the connections between the sides are dense? Seems like finding those disconnected sets would be much harder in that case.
That's where alignments come into play. If the connections are dense, they can use the alignment properties of the model to strategically split two paths on the A side into multiple segments.
So instead of finding the anti-complete sets directly, they manipulate the structure to create something new. It's like a mathematical puzzle, shifting the pieces around to reveal a hidden pattern.
A brilliant analogy. And these segments, because of the way they were created, form an induced complete bipartite minor model, one of those specific structures that can prevent large anti-complete sets.
So it's a beautiful if-then-else structure. If the connections are sparse, they find the anti-complete sets. If the connections are dense, they find a structure explaining why those sets can't exist.
Exactly. And with that, the proof of theorem 2.1 is complete. They've demonstrated that any sufficiently complex graph, free of those special structures, must contain two large anti-complete sets.
It's amazing how they weave together all these concepts, Treewidth, Ramsey theory, strong blocks, those unique interrupted constellations, and those half-induced models. The proof is truly a testament to the power of mathematical thinking.
I agree. By carefully defining concepts and applying logical reasoning, we can unravel these complex relationships and get a deeper understanding of the structures around us.
This deep dive has been incredibly illuminating. But even with this comprehensive answer, I suspect there are more questions to be explored. It feels like every answer in mathematics simply unlocks more questions.
You're absolutely right. And in that spirit, the paper concludes with a thought-provoking question. Remember those interrupted ORS constellations? The sneaky exceptions. That forced us to refine our initial understanding.
Of course. They almost slipped through the cracks.
Well, the authors challenge us to consider whether other even more complex structures might also serve as exceptions to theorem 1.4. It's an invitation to continue exploring and pushing the boundaries of our knowledge.
I love that challenge. It reminds us that even with powerful tools and theorems, there's always more to discover in the world of mathematics. It's a never-ending journey of exploration.
Indeed, the landscape of mathematics is vast and ever-evolving. Every new discovery opens up new horizons and possibilities.
Well, on that note of endless exploration, I think it's time to wrap up this fascinating deep dive. To you, our listener, we encourage you to read the full paper. If you're eager to explore the intricate details of the proofs, it's a rewarding journey for any math enthusiast.
It is.
Until next time, keep diving deep and exploring the wonders of mathematics. And remember, even in the most complex structures, there's often a hidden beauty waiting to be uncovered.